Hi, so this is a completed integrated plant terrarium circuit. The purpose of this video is to highlight the control interface used to work the circuit. So I'll start the simulation. The LCD highlights it's the integrated terrarium system. So when I click on, for instance, number 1 on the IR remote, it displays this is the brightness mode. It will then say LED on. The LED is on because the brightness is at a really low level. If we put this brightness up to a high level and click 1 again, it shows this is the brightness mode, and now the LED is off, and this is showing the LED is off on the circuit. This is also represented in the serial monitor, as it shows mode 2295, which is number 1 on the remote. It then shows the brightness it was at, then the LED being on or off. Again, we'll go for another option, so we'll go for option 2 this time. This is air mode with the gas sensor. The fan is on. This is because the CO2 levels are really high at the moment. If we move these levels away and click on number 2 again displays this air mode, but now fans off because the CO2 is not close. We'll do this for number 3 as well, which is temperature mode. Again, LCD displays temperature and the fan's off and the heating's on. Turn this up. Temperature mode again. As you can see, the DC motor is on to increase or decrease the temperature. And finally, button 0 is the soil moisture. It shows the moisture level is 17%, water is required, so the water pump is on. This shows that by using this remote, by clicking 0, 1, 2 or 3, it can take us to the particular subsystem, and then we'll complete the outcome of that subsystem. And then this is shown in the LCD monitor and the serial monitor, the results of this. So this is the online simulation of the soil moisture subsystem on Tinkercad. When I start the simulation, the LCD displays that is the soil moisture system. For this subsystem, I have had to use a potentiometer instead of the soil moisture sensor, as that is not available on Tinkercad. So in the simulation, it shows that the soil moisture level is at 12%. This means water is required, and this is established on the LCD monitor and in the serial monitor as well. Because of this, the DC motor is now running to put water into the soil. When the percentage is increased to 39 and now 64, because this is over 50, and between 50 and 67, it means the moisture level is suitable, and this is displayed again in the LCD monitor and the serial monitor. Also, because of this, the DC motor is turned off as water is no longer required. And finally, for the last outcome, is that when the level is even higher, the LCD monitor displays that there's a water excess and there's too much water, so the DC motor is also again turned off. Simulation stopped.
Hi, so this is the physical circuit for the soil moisture subsystem. As you can see right now, the soil moisture is at 14%. It's in a dry area. So this means water is required for the soil. So when I put the battery in, the pump will go. Let's see. So that's going. Because it's a low level. When I apply the soil moisture sensor to a wet area, you can see the number going up. It is now turned off because it is at a suitable moisture level.
Hi, I'm Cameron and I'm responsible for the creation of the temperature subsystem. On the right side of the screen you can see the circuit, which includes two relays for each subsection of the system. The side on the left, so this section here, is the fan section, which is represented by a DC motor, and on the right side is represented by a resistor, which is the Peltier heating element. This system also includes a temperature sensor, as well as two LEDs here, which help with user interaction, as when the fan's on, for example, this one will turn on, and then when the heater's on, this side will turn on. This just helps with the user kind of understand what parts of the system are working without having to look into the terrarium, as well as just makes it more aesthetically pleasing as well by having the kind of visual cues there. Lastly, the whole system is powered by a 9-volt battery, which can be seen here. So in order to design the subsystem, a block diagram and a flowchart was created. So the block diagram represents the kind of inputs and outputs of the system. So you've got the temperature sensor, which is reading the temperature of the environment, going into the Arduino device, and then the outputs are the Peltier device and fan being turned on, as well as the LED visual output. In terms of the flowchart, this was used to help break down the logic of the subsystem by putting it into different subsections, which was then used as a basis to create the code. There were four main specification points related to the temperature subsystem. These were that the temperature cannot exceed 25 degrees or go below 21 degrees. This was just to allow the coffee Arabica plant to grow, as this was the perfect environment for this. The other three relate to the components, so the system had to use a Peltier device, it had to include a fan, and it also had to include a temperature sensor, as these working together would allow it to cool, heat, and the temperature itself to be read. Final stage in the process was to test the actual temperature subsystem itself. So this was done both physically and virtually due to limitations from the COVID-19 pandemic. So in terms of virtual testing here, you can see that the system worked correctly. So when the temperature was too low at 9 degrees, the resistor here was turned on, which can be viewed by the reading from the voltmeter here. And then when the temperature was too high, the DC motor here is turned on as the RPM is really high. This will be discussed in later as well when there's a video representation of this occurring. In terms of physical testing, so it was just a small part of the system that was tested, so it was just the fan section and as well as the LED for the fan. This will also be discussed in the following section. So this here is the simulation within Tinkercad, and this is the virtual simulation. So the temperature here is set to 21 degrees, which is within the range of 21 to 25 degrees, so the plant is going effectively, and therefore both the heater and the fan are turned off. If I was to turn the temperature to a lower temperature, so below 21 degrees, then the heating element turns on, which is represented by the resistor here, and can be seen with the LED turned on, as well as the reading from the voltmeter is high. And if the temperature is turned to 118 degrees, for example, the fan will turn on, which is represented by this DC motor as well as the LED. And as you can see, it is turning right now. Circuit that was created for the temperature subsystem. And as you can see here, the temperature has risen and then went back down many times. So I'll now example this by holding onto the temperature sensor to heat up, which can be exampled here. And this turns on the system. And I'll now let it go to let this temperature go back down again and show that the system turns off when it is not required anymore. There we go. So then, as you can see here, it was plotted on the graph.
Okay, so here I have my CO2 sensor circuit diagram created in Tinkercad. As you can see here, the Arduino, my code is created here when I said that if if the sensor measures a CO2 value above 500, the fan will be turned on. So as you can see, I start the simulation, and the sensor just measures the CO2 values. If I put it far away of the sensor, it measures low CO2 levels, but if I take it near, the levels will increase, and then the fan, in this case um, a general motor chosen, will turn on.
I'm Emma and I was in charge of designing the light subsystem for the terrarium. I recognised the specifications for the light subsystem was to control the light based on the surrounding light the plant was given. This led me to create a circuit that included an LED and a photoresistor. Once created the circuit on Tinkercad, I began simulation testing. To program the circuit, I used an if-else statement with a global variable defining brightness thresholds. This worked well, and although it took me a few attempts to get the wording of the code right, I am happy with the final outcome as the code works successfully, as you can see in this video. After completing the Tinkercad simulation, I tested the code on an Arduino circuit board provided by the university. The board provided by the university consisted of an LED, photoresistors and suitable resistances. I copied and pasted the code from the Arduino into the Arduino software, connected the circuit to my PC and uploaded the code to the circuit. At first I realised the code worked, but the timing between code loops was too long, so left me wondering if it did work, but it just took a while. So I changed the timing from 9600 milliseconds to 3600 milliseconds. This worked much better with the reduced waiting time, as I was able to see my code working with the circuit much quicker. As you can see in the video, there's a suitable amount of surrounding light and the LED stays off. But when I cover the LED with my hand and the light is reduced, the LED turns on. In the integrated design, this allows the plant to receive light 24 hours a day to ensure maximum growth potential. After completing the Tinkercad, for the integrated report, I was also in charge of the CAD modelling for the terrarium. The shape of the model was actually based on a takeaway coffee cup idea to go with our coffee Arabica plant. The model consists of three main parts as seen in the exploded view on the right hand side. The lid, which holds the Arduino circuit, all the sensors and the LCD screen. The lid is basically the main hub for all electrical components for this design. The main cup section is one manufactured part, but the base is higher so that it acts as a lid for the water tank below. The main part of the terrarium will house the soil and plant and is easily accessible through the lid opening. The base also holds the water for the water pump to automatically water the plant when sensors detect soil moisture is low, and the base also has quite a sturdy shape to ensure terrarium is stable and won't fall over.